Suppose x is a random variable that models waiting time for an event. In a perfect world, the longer you wait for x, the more likely it will occur in the near future. The universe has a memory of how long you've waited. We sometimes live in that world. Suppose the waiting time for a parking space is uniformly distributed over the interval from 0 to 30. Find the probability that you'll wait more than 10 minutes and the probability that you'll wait more than 10 additional minutes, given that you've already waited 10 minutes. The probability density function is, and so the probability that x is greater than 10 will be Now, if you've already waited 10 minutes, then waiting an additional 10 minutes means you'll have waited more than 20 minutes altogether. So we need the probability that x is greater than 20, given that x is greater than 10. So our conditional probability formula tells us that this is, but the probability of the conjunction is just the probability that x is greater than 20. And so this probability will become, and we find the probability x is greater than 20. We've already found the probability x is greater than 10. And so we find, and that gives us our conditional probability. Intuitively, we can see that the probability of waiting 10 minutes more can't stay constant. If you've already waited 20 minutes, then you're guaranteed that you'll wait under 10 more minutes. So the uniform distribution has a memory of how long you've waited. The memoryless property is equivalent to the conditional probability that if you've already waited some amount, then the probability that you'll wait some additional amount t is the same as the probability that you'll wait that amount t. So suppose the probability that x is greater than t is given by some function. The probability that x is greater than s will be, and the probability of the conjunction, well, that's really just the probability that x is greater than s plus t. And so that will be, and so our conditional probability will be. And so if we want these two probabilities to be the same, we need for all values of s and t. And this gives us a way to characterize all memoryless distributions. So suppose the cumulative distribution function for a random variable is x memoryless? So we can find g of x, that's going to be 1 minus f of x, which will be, and then we can compare g of s plus t to g of s times g of t, and we find those. And since g of s plus t is not the product, then x is not memoryless. Or let's consider another example. Now, while we could compute g of x equals 1 minus f of x and check to see if g of s plus t is g of s times g of t, the important thing to remember about the memoryless property is, I forget. Oh wait, that's right. The past doesn't influence the future. If we imagine x to represent the waiting time to an event, then in this case the probability that x is greater than 1 is actually 0. So this event must occur sometime before x equals 1. Consequently, this distribution can't be memoryless. And again, a good way to get insight into math is to solve it again. So what if we split x into 1/2 plus 1/2 and compare the probability that x is greater than 1/2 plus 1/2, given that x is greater than 1/2, to the probability that x is greater than 1/2. If x is memoryless, the two probabilities have to be equal. Again, the probability that you're waiting an extra half shouldn't depend on how long you've waited already. But since the probability that x is greater than 1 is 0, that first probability is 0, while the second is non-zero. And so they can't be equal. Okay, fine. We'll use the formula. G of x is 1 minus x, so g of s plus t is, and g of s times g of t is, and clearly the g of s plus t is not the product of g of s times g of t. Could there be other distributions that are memoryless? Let's see if we can find one that is non-zero for non-negative values of x. In other words, the probability that our random variable is less than 0 is 0. Now remember, calculus is easier, so let's also assume that a cumulative distribution function is differentiable. So let our probability that x is less than some value be 1 minus some function. So our probability that x is greater is that function. And suppose g satisfies that multiplicative property. Now, since this has to be true for all values of s and t, suppose that t itself is 0. Then g of s plus 0 must be g of s times g of 0, which gives us, and so g of 0 equals 1. You might be a little suspicious here because we're doing that dividing by something that makes us a little worried in ordinary algebra. But remember, the only alternative here is that g of x is 0 for all x, which won't work for a cumulative distribution function. Now, again, a useful thing to do when you're learning mathematics is to prove it again. So here's a second proof that g of 0 is 1. We have our cumulative distribution function 1 minus g of x. So f of 0 is 1 minus g of 0, and so that's the probability that x is less than or equal to 0. Now by assumption, the probability that x is less than 0 is 0, and since this is a continuous distribution, remember we assumed it's differentiable, so it has to be, we can ignore the equality, and so the left-hand side is just 0, which tells us that g of 0 must be 1. Now, the reason calculus is easier is we can always introduce the derivative. Now, the easy thing to do would be to differentiate both sides, but the problem is there's two variables here, s and t, which is going to complicate things. So instead, let's use the definition of the derivative. So let s be x and t be h, which gives us, and we'll do a little bit of algebra here. We'll subtract g of x and then divide by h. And now we'll introduce the calculus. We'll take the limit as h goes to 0. What's that? Question in the back?
Isn't h limited to positive values?
Well, that's true. We should require that h goes to 0 from above. But remember, we're assuming that the derivative does actually exist, which means we know the limit exists, which means that we can find the limit any way we want to. So we can ignore that problem of whether h should be positive or negative. So the left-hand side is just the derivative. The right-hand side, remember, g of x is actually a constant in all of this because h is going to 0. So we can remove that as a common factor. And remember that g of 0 was 1, so this becomes, and so now this limit is the derivative at 0. And again, we're assuming that g of x is differentiable, so g prime of 0 is some constant, which we'll write as negative lambda. And the reason that this is negative, remember g of x is the probability that x is greater than a certain amount, which means it should be non-decreasing, and that means the derivative will be non-positive. So we can introduce the negative, and that way lambda is either 0 or some positive number. At this point, we can use a little bit of differential equations. Negative lambda is the quotient, and we can integrate both sides. We get log, do a little algebra, and we have some appropriate constant c1. And again, we know that g of 0 is 1, so our constant has to be 1. And putting everything together, this tells us that the exponential distribution is the only differentiable memoryless distribution.